You're good. Great.
Fantastic. All right. Thank you so much for everyone for making the time to this talk, and thanks, Arya, for the invitation and introduction. Today, I'm going to talk about accelerating non-convex optimization via online learning. I apologize in advance if it's not a proper keynote talk. There's not much of vision or future and stuff like that. It's just a recent result of mine with my group. And so I space enjoyed to work with my students, Roichen, Chujiang, and Francisco. Yeah, let's jump into the problem. We're minimizing a function, deterministic, smooth, and I'm going to define how smooth the function is throughout the talk. The important thing to remember from this is D is the dimension of the problem. All right, classic old school problem, everything is deterministic. All right, and the important thing about this talk is that I'm going to assume only access to gradient information, no access to higher order information because of obvious computational reasons, right? And what's the goal? The goal that I've been chasing for the last few years, I would say it all the way goes back to my PhD, is that can we show globally and provably the use of preconditioner or curvature estimation can lead to provable gain over classic gradient-based. A very basic problem, question. And when I say preconditioner, I mean when you pre-multiply your gradient by a matrix that you hope that it does something else, your object. All right, so throughout this talk, I'm going to first briefly talk about our result for answering that question in the strongly convex and convex case very briefly, like 5 minutes. And then I'm going to focus mostly on a very recent result that was on answering this question for the non-convex case. And then I'm going to spend the majority of the talk on the algorithmic details of how we get the result. And then finally, I'm going to finish by talking about upper bounds and lower bounds for the non-convex case and some open problems. All right, so if you want to use preconditioner to get improvement, first we need to understand what we would get just on basic gradient types methods. And again, these are all textbook results that you all know. We know that if you're in the smooth gradient Lipschitz and strongly convex case, GD, gradient descent, accepted gradient descent, they give you a linear rate, which depends on the condition number or square root of the condition number of the problem. And in the convex case, you either get 1 over k or 1 over k squared or GD and AG. These are sort of textbook results. And our goal was to improve these bounds. All right, so is it possible to improve these bounds only using first order query? And if you have read this paper by Nesterov and the textbook results, we know that it's impossible because there's a lower bound, and we know that AGD, accepted gradient method, is worst case optimal in both the strongly convex and convex. Even if I give you additional condition that the Hessian is Lipschitz, still the same thing holds because all the lower bounds are using quadratic functions, that doesn't help. So there is no hope to do that. What am I talking about today? So the key thing is all these lower bounds are heavily using the fact that number of iteration is larger than dimension. If you look at all those constructions, k is larger than d. K is less than d, right? So, and because of that, sort of like the dimension is sort of like is too high that I never reach that, right? So that's why the preconditioner could never help you, because for preconditioner, you need at least d iteration to figure out where you properly estimate the matrix, right? So given the fact that these lower bounds hold for k less than or equal d, what would be the ideal situation for a preconditioner method? So there is hope to improve first order methods for k larger than d, but we know that for k less than d, we cannot improve them. So the ideal scenario is I give you a method that in the first d iterations, it would match AGD, and after the iteration, hopefully it gives you something else. That's the goal of this. And in the strongly convex and convex case, we managed to obtain this result. I'm going to mention them in the next slide. But to obtain this result, we sort of like took this online learning guided quasi-Newton proximal extra gradient approach. A lot of fancy words. What do they mean? I'm not going to spend time on talking about this algorithm because it's for strongly convex and convexity. I'm just going to give you a high-level idea of what we did. Instead of going for the classic template that all the preconditioner methods are doing, which is sort of like mimicking Newton's method, we tried to mimic Newton hybrid proximal extra gradient method, which is the optimal second order method. If you had access to Hessian, the optimal method is not Newton, it's not cubic regress Newton, it's not accelerated cubic regress Newton. It's accelerated Newton HP by Montero-Slater, which gives you 1 over k to the power of 3.5. We try to mimic that. But most important, and you're going to see that in the non-convex case, we're also going to do something unconventional to construct our general update. And for the update of Hessian approximation, unlike classic approaches that they're trying to do B to take the preconditioner or B in a way that it mimics the Hessian, we didn't try to do that, and we let the analysis guide us how to pick B. And nicely, it ended up being an online learning problem in the space of matrices. So to update B, we saw an online learning problem in the space of matrices. And using these two pieces, we managed to get this result for the strongly convex case when the gradient and Hessian are Lipschitz. So basically, it has two bounds, a linear rate and a superlinear rate. And the superlinear rate becomes better than the linear rate exactly after C iteration, and C in the worst case can be the dimension of the problem. So in the first iteration, you get a linear rate that you would get with gradient descent, and then after that, you get a superlinear. In the convex case, we got an even better result because it could be technically 8GB. So basically, in the first d log d iteration, you get 1 over k squared. And exactly after d log d, you would get a rate that is faster than 1 over k squared. Okay. Again, that's the best we can hope. I mean, whether this is good or not, whether we can do better than 2.5, I don't know. But all I can tell you is that you shouldn't be able to do better than 3.5, because 3.5 is achievable only if you have access to exact Hessian. And the fact that you have to wait for the iteration, it makes sense because of the lower bound. But here we have d log d slightly gap, which hopefully can be resolved later. All right. So in summary, I wanted to spend this 5 minutes, 10 minutes to tell you that at least for convex and strongly convex, we realize that there is possibility to provably and globally outperform AGD if you wait for the iteration. Or if you think about it, in this case, if D is less than 1 over root epsilon, epsilon being the required x. So if you're in the moderate D regime, there is hope for preconditioners to hold. But if you're in the D very large regime, there's no hope because of all these lower bounds at B. I gave this talk over the last 2 years, and I was quite happy about it. But then you go anywhere, you give a talk, yes.
I have missed this, but what is the computational cost of the
That's a great question. So I don't have it here for this for strongly convex and convex case, but everything is in terms of matrix vector products, right? Everything is order d squared. But the only thing that I care about is gradient query, because the lower bounds are in terms of gradient queries. It's not about computational cost. But anyway, I have the overall cost in terms of number of matrix vector products in addition to gradient computations that we have. And of course, then it's the battle whether the matrix product is costly or not. And the matrix product is always, matrix vector product is always d squared, while the gradient could be nd, where n is the number of samples. So if you're in the moderate dimension regime, nd is the dominating term, not d squared. Like if your n is larger than number of parameters.
And e to the power 3.5 lower bound that you mentioned, that is only, that's for Hessian queries.
Yes, if you have exact,
With gradient
there's no
queries.
way we can reach. All right, so, okay, that was cool, but everybody was asking about the non-convex. You know that only non-convex matters, which is fine. So, but we try to address this problem. Okay, so what's the most basic goal to solving non-convex optimization? You want to get a point that its gradient is less than epsilon, right? Because of course you don't have global optimality. Cool. So if you want to understand that there is hope for improvement, first you need to understand what are the upper bounds, what are the lower bounds. So if you only have gradient Lipschitz, and you want to get the first illustration point of a non-convex gradient Lipschitz function, gradient descent gives you 1 over epsilon squared. It's actually L1 over epsilon squared. And in fact, this is optimal, worst case optimal, due to several results. Most importantly, this lower bound, in this beautiful all 2003 paper, it's dimension independent. No matter what your dimension is, there is no hope. So there's no such regime that I can say, hey, if D is small, I can beat that. No, there is no hope. So there's no hope for preconditions to help you in any way. All right, so that's sad, but it makes sense. You need for quasi-Newton, for like precondition-based method to help or work, you need some regularity condition on the Hessian, similar to the result for convex and strongly convex that they had. So what if the Hessian is also Lipschitz? So I have access only to gradient, but the gradient and Hessian are Lipschitz. And I'm not the first person who looked at this problem. I vividly remember that in 2017, when I was wrapping up my PhD, these two papers came to archive around the same time, within a few days from each other. And completely different ideas. They managed to show that we can get 1 over epsilon to the power of 7 over 4 log 1 over epsilon, which is of course an improvement over 1 over epsilon. One is this stock paper that was the whole idea was how to approximate cubic regularized Newton method using matrix vector products to get something better than 1 over epsilon squared. and they need Hessian vector products approximation and stuff. And this was this beautiful paper by Eric Common and his collaborators that they showed that using a clever version of accelerated gradient method and combining that with negative curvature idea, you can actually get similar results. This was ICM of 2017. So these two papers show that if you have only access to gradient and you have these two assumptions, you can get better than 1/2 square. That's nice and interesting. But in 2022, somebody managed Lee and Lee in ICM 2022. That was the first progress after these 5 years. They managed to shape the log factor using a very clever restarting idea. So this is the best upper bound that we know. 7/4 without the log term is the best upper bound that we know for this setting. What's the lower bound? The lower bound is 12/7. There's a gap. I'm going to talk about the lower bound towards the end of the talk, but I'm just telling you that there is hope for improvement. And what we try to do, we are trying to see if using all these nonsense I'm talking about, condition stuff, can I beat this 7/4? That's the game. Okay. And this is the result that we got. So we basically say that if the gradient Hessian are Lipschitz, we have a method that has this complexity. I'm going to ignore the terms that depend on L1 and L2. I'm just going to give you the final result. It's D1/4 epsilon to the power of 13/8. So if you ignore the D term for a second, 13/8 is better than 7/4 because 7/4 is 14. So that's good. But we have D dependence. So we're not always better than the previously best known bound. You're better if D is less than 1/√epsilon, which is not super bad assumption. If D is moderate, less than 1/√epsilon, this probably beats 1/epsilon to the power of 7/4. And that's sort of like the most recent result that we have. And at a very high level, to solve this problem of finding a stationary point of a non-convex system problem, what we're going to do, we're going to design a quasi-Newton algorithm that incorporates solving two online convex optimization. The first online optimization problem is basically related to this notion of online to non-convex conversion by Ashok and his collaborators, that they showed that the task of finding a stationary point of a non-convex function can be translated into this task of solving an online convex optimization. It's a very beautiful framework. I'm going to discuss it in detail. And then to solve that online convex optimization problem, I'm going to introduce an optimistic quasi-Newton method, where the Hessian approximation for the quasi-Newton method itself is another online learning. So you have to deal with two online learning problems to get the algorithm and then eventually get the complexity bound that they have. I think a good talk should tell you what's the problem, what's the best known bound, what's the new result, and how you get the new result. So I answered it, like the problem is getting normal gradient less than epsilon when gradient and Hessian are Lipschitz. The previously best known bound was 7/4. We got D/1/4, 13/epsilon to the power of 13/8. And in the remaining of the talk, well, it's like 25 minutes, I'm going to bore you with how we get these bounds.
So the lower bound also has the Lipschitz from.
Yes. Because the lower bound for without Hessian Lipschitz is one of those things. I'm going to talk about the lower bound. Any question about the problem, result, how we get our general thing? All right, so
The idea is this is like where you should aim go to, like 1 for epsilon.
I'll talk it to her. And the concluding remarks, I'm going to tell you what are the open problems in terms of upper bounds and lower bounds for this. Okay. So in detail, I'm going to discuss. So now I'm going to spend the rest of the talk telling you what are these two pieces of puzzle to get this improvement. Okay? The first thing, as I mentioned, is this online to non-convex conversion. It's a very elegant framework, again, as I said, by that paper, the ICM 2022 paper. So I feel like in general, it's a good thing to learn, but for other purposes too, so I'm going to spend some time on it. Basically, the task of finding a stationary point of a deterministic non-convex function can be perfectly written as task of solving an online convex optimization. To do so, I just follow this very basic idea. Any optimization algorithm that you do, you're picking your next point as xn minus 1 plus some delta n for some, analytical reason. Assume that the step is bounded by it. Okay, that's all I'm going to assume. Right? So what is your goal in optimization? Your goal in optimization, in non-convex optimization, is to pick this animal in a way that it maximizes the function difference. Right? That's the whole game of non-convex optimization. But instead of picking delta n using something that I think is the right thing, I'm going to let the convergence analysis tell me how to pick delta n in order to maximize the function value. Okay. I'm sure you all have seen this in calculus 1. You know that the function decrease, if you take this a step, if I take this a step, the function value at xn and xn minus 1 is exactly this, the inner product between the difference of the variable change times the average gradient over the segment of xn minus 1 and x. That's it. Okay, so if I had this animal, which is average gradient over the segment, the best action was obviously delta n being this gradient divided by its norm times d, because I want to keep the norm to be d. That would be the best action. That would lead to the maximum function decrease, right? But I don't do it. Why? Because two reasons. I don't want to compute the integral. I want to compute the integral. I don't have to take anything complicated in non-convex optimization, let alone talk taking the integral. So I don't want to take the integral, but the bigger problem is I don't know anything about that segment when I'm picking delta. I just know xn minus 1. I don't know the next point, let alone any point in that segment. So that information is not given to you at the time of selecting delta n. Okay, so how can I resolve that issue? To resolve that issue, you can say, hey, I'm going to approximate the gradient over this segment with the current gradient. That's something that I've access to, which happens to be exactly what you do with gradient descent. It's easy to compute and available at the beginning of iteration. And if you do so, you're approximating this integration of the gradient by something that has error of order L1, the delta. And even if I give you second order smoothness, you cannot get a better bound. So it means that the equality becomes inequality, and you have an additional error term. You know this better than me. If I replace delta n by this direction and optimize for d, I would get just 1 over root t or 1 over epsilon squared. So the thing that we all know. So gradient descent would give you 1 over epsilon, 1 over root epsilon. Okay. So that's not satisfying at all. So, but if I tell you that the Hessian is Lipschitz, you yes.
Oh, the true count.
What, this bound?
Yeah, we also it's divided by 2 count. So you divide like L1, which is yours, L1 divided by 2. So where does
Oh, here, yeah, that's an error here, actually. No, it should be only here, no.
Oh,
Or actually, maybe it's not under. No, actually, because it's an integral of 1 over 2 is short.
equal over T.
Doesn't matter. But the important thing is, if I tell you that the Hessian is Lipschitz, you can do a better job than for approximating that integral. And the better thing to do is to look at the point that is literally the middle of the segment between xn and xn minus 1. So if I replace the integral by the gradient at the middle point of the segment, I can show that the gap between that average over the gradient of the segment minus my predictor, which is the gradient at the middle point, would be at most over L2 delta n squared. Now I have delta n squared, which is much better because delta is small, so my error is going to be smaller, and it depends on L2, the second level of Lipschitzness. So if I manage to get the middle point between xn minus 1 and xn, suppose I had a genie that could tell me what would be the middle point. And if I replace that equality with this new bound that I have, and replace delta n by, again, minus of that normalized times d, I would get 1 over t to the power of 2 over 3, which is 1 over epsilon to the power of 3 over 2. That's a huge. 3 over 2 is the rate that you would get if you do cubic Arrhyes-Newton. So there is no hope to get that. What am I doing here? That doesn't make sense. I'm computing something that I don't have access to. But it's just a better approximation. I replace the integral with the middle point. If I had the middle point, I would get this nice result. But however, I don't have that middle point of the segment. But it resonates a lot with online learning, right? I pick delta n. I wish I had the middle point. I don't have it, but I wish I had it. And then I see how off I am from this, which was what I would have taken if I knew that middle point. Then I calculate the regret and so on. So you can think of picking this delta n at a high level as an online learning problem. But the question is, what would be the loss? Some boring math. So if you look at that inequality, and you add u as your competitor, you're going to have a term that shows the loss of your competitor after t iteration, gn being the middle point of each segment. So if I have seen all these steps, the best fixed action would be the sum of all these average gradients normalized times d. That would be my competitor. And then the regret that I'm going to suffer is like how I pick delta times and how off my loss is compared to the loss of that competitor. And the nice thing about this analysis is that the average of gradients of the middle points, if I look at those average gradients, they're upper bounded by constant, a term that is like online convex optimization. So all I have to do is to solve this linear loss online learning problem to get a complexity bound for a non-convex optimization. I don't, is it clear? I don't like this. Why? Because it's average of gradients. Average of gradients is 9 points. I want gradient of average point. Because it doesn't give me a gradient at a single point that is nice, right? So I have to transfer this to the gradient of average point. And if I do that, I can show that the gradient at the average point of all these W1 to Wn is bounded by average of gradient plus a term that depends on how much you're drifting, right? T is the number of iteration, D is the steps. And if I do so, I will get a clean bound now. Why? Because I'm saying that after any step, if I look at the average point, I look at its gradient, it's bounded by a constant, bunch of two other constants that I can optimize for at the end of the analysis, and a regret term that is online convex optimization. So now all I have to do is to solve this online learning problem. That's the picture. So you start from x0, you pick a decent, you pick a delta, and you see the middle point afterwards. And then you keep going after t iterations. This is the average point, and this is the competitor that you would have. And this would be a complexity bound for an algorithm to solve a non-convex optimization. Any question about this? So we can write the non-convex problem as a complex. It's all. All right, there's one small technicality I'm going to bore you with. Again, this is the last piece, I promise. If I do this approximation, each time I have to pay a price of t squared times d squared, which I don't like. It's the length of the episode. So the longer the length of episode is, the gradient of average is farther from the average of gradients. So for that reason, I restart the algorithm every t iteration, and I'm going to have k episodes. So if I have the total of k times t iteration, it's involved of k episode. Each of them has a length of t. And in each iteration, I'm going to look at the average of that episode. And my competitor is not going to be a fixed one. Each episode has its own competitor, which is the average gradients in that episode. So if you do this minor modification, your regret would become your complexity. Your regret would be basically accumulation of the regrets over k episodes, right? And the bound that you would get would be average of the gradients at the average. So it gives you 1 degree of freedom, right? I could have just said that, hey, kt is just t, and then I wouldn't have another parameter. But the important thing with this sort of like episodical thing, here instead of having k squared, t squared, I have t squared. So I can control how much I'm drifting from the average. The minor details doesn't really matter. The heart of the matter is, the first part of the whole idea of this algorithm is that we're solving a non-convex optimization problem, and that's all I'm going to do. I'm going to pick a delta time with bounded norm group, however you want to pick it. And then I'm going to look at what's my next point. I'm going to compute the middle point and its gradient. And I'm going to judge you by seeing that how off you're from, your loss is going to be Gn transpose delta. And Gn is being the gradient of the middle. And your competitor would be the average of gradient over that episode. You want to minimize this regret. If you minimize this regret, you get a better upper bound. As a result, you get a better complexity for solving non-convex problem. All right? That's pretty much it. Now, to minimize the regrets associated with this online learning problem, all you have to do is just pick an online learning algorithm to solve it, right? That's a conversion that they did, and then the rest is sort of like should be easy. But you're going to see it's not as easy as you might. In this stuff, I'm going to use optimistic methods to solve this online problem. Okay. And I'm sure you're all familiar with optimistic method. We have seen the use of that for online learning, min-max optimization. But I'm going to bore you by just telling you what's the main idea of optimistic method, and then to set the notation and the definitions. So the whole idea of optimistic method, it has some connection with control theory as well. You predict what would have been your actual gradient. But you see that you are off by a bit, and then you use the difference of your last prediction as a correction term. right?
The quick question, the way you set up the loss, it's the inner product of Gn and delta n.
Right.
So you want to align Gn with
No,
delta n.
minus of G. Yeah.
Oh, minus of, oh,
I
okay,
mean,
okay, okay, I
if
see.
you were G and you would give the middle point, and I could obviously give the middle point, I would pick the minus G.
Minus G, yeah, that's why.
Normalized by.
Okay, okay.
All right. So the catch here is I don't know Gn. I assume Hn is a hint. And I'm going to use that hint to update my iterate, but I'm not going to just use the Hn because it could be way off. What I'm going to do, I'm going to subtract the previous error of my prediction from that. The whole logic of optimistic method is that I'm hopeful that the error at round n is close to the error at round n minus 1. So I can say that the best predictor of Gn is the current predictor plus the error of the last. Right? This is the prediction, this is the correction. That's the idea of optimism. All right. So, and I haven't said anything about Hn. Hn can be any vector. The key point is whatever Hn I pick, this would be the regret level. Right? That's all that matters. It's the gap between Gn and Hn, obviously, how well you predict the middle point, minus this term that is going to come handy, and it shows like how much you have drift between your equation. All right, so that's my regret if I just go with any optimistic method. Now it's going to get fun. So all you have to do is to pick Hn to be close to G. Okay, if I'm at xn minus 1, and previously I picked xn minus 2, and this was my middle point, now I want to pick delta n, right? And I wish I had the gradient at the next middle point. I don't have it. What's the best predictor of the gradient at the next middle point? The natural hint. The previous middle point's gradient, right? So if I predict that Hn, the hint, is the gradient at the previous middle point, and I use that as my hint in the optimistic method, the gap between Gn and Hn, your predictor, would be something of 1/2 of delta n minus 1 and delta n times the Lipschitz continuity of the gradient. So you end up paying something like L1d. Right? So if I predict the next middle point gradient with the previous middle point gradient, I would end up with an error for the L1d. And if you put this error in the circuit down, and then get the final result that would appear here in this complexity, if you do all those calculations, balance all those eta, dt, everything, you would end up with a complexity of 1/epsilon to the power of 11/6. I'm sorry. 11/6. Which is nice. It's better than 1/epsilon squared, but it's not better than 7/4. So it's not like a very good hint, but it's better than just doing gradient this. So you get 11/6. What if I do something slightly smart? Basically, instead of predicting the gradient at the next middle point with the gradient at the current middle point, I would say, hey, I'm even further optimistic. I feel like delta n and delta n minus 1 are close to each other. If delta n and delta n minus 1 are close to each other, if I assume that's true, then the next middle point would be here, right? Because I would keep going this way, and the middle point would be here, right? So I can approximate the gradient of the next middle point with this Zn minus 1, which is basically assuming that delta and delta n minus 1 are close to each other. So that increases the cost by a factor 2, because now I have to compute gradient at another point that was not part of my trajectory. But that's fine, factor 2, who cares? Complex. It's absolute constant. So if I use this as my hint, now the error of approximation depends on how much delta n is close to delta n minus 1. So instead of plus, you're going to get minus. And because of the fact that in my regret term, I had this negative term, I can deal with this using this. And instead of 11/6, using this better hint function, I will get 7/4. So look, 2017, those two papers use completely different ideas to get 7/4. And if you read those papers, they're quite long and messy to deal with.
Where did you use the Hessian Lipschitzness?
The Hessian Lipschitzness is basically the heart of the matter from the very beginning, because look at it. So even to get this regret bound, we're using it several times. But not for that hint function. For the hint function, I'm not using L2, I'm just using L3. It's a good question. So anyway, this very simple algorithm, first order optimistic method to solve that regret analysis. Like if you look at the order, it's just 2 lines. It will give you 7/4 without any sweating. And trust me, I've seen the proof, it's less than a page. Beautiful. when I saw this, I was like, this is great, but it was very unsatisfactory because it doesn't give you a better bound. It still recovers the 7/4 that we have from 2017. But given this framework, this online to non-convex, using the optimistic methods, can we do something using this curvature estimation idea to get something better than 7/4? Okay. So basically, for the sake of argument, again, I'm not going to have access to Hessian. I'm not going to have access to Hessian. But suppose I had access to Hessian, right, Arya? So if I had access to Hessian, I know that the good hint would be the gradient at the next middle point. But if I have access to Hessian, I would look at the Hessian at that point and basically linearize the gradient around this point that I know is a good. And I would use this hint. The catch here is that the hint itself depends on delta n, which is implicit. We don't have access to it. But roughly speaking, that's what I would delta. And if I use this hint, assume that I can do this, I would get a better, I would get an L2 error now, going back to your point. And then it would lead to 1/epsilon or 3/2, which is the optimal complexity for second order. The previously known algorithm that achieved this bounds is cubic quasi-Newton method, right? But this is a completely different framework, has nothing to do with cubic quasi-Newton, and gives you 3/2, which is also optimal for second order. So if I had the Hessian, this framework would give me the optimal method. So I know I'm on the right track. So there, because there's a lower bound knowing that 3/2 is optimal. Okay, what are the issues with this hint function? The number one is I don't have access to Hessian. So I'm just going to replace it by some b. And I'm not going to assume anything about b, it's just an approximation of Hessian. And then the second issue is delta n is not known, but it's fine because it's like a quadratic function. So it's basically solving this implicit problem is equivalent of solving, sort of like matrix inversion, but you have a constraint, so it's equivalent of solving the trust region problem, which I'm going to briefly mention in the next slide. It's not a big deal because it's just a matrix. It's not any nonlinear function. All right, cool. So I'm just going to first explain how I deal with this issue. Again, if I use this hint function, I'm going to have delta n plus 1 here, right? And delta n plus 1 here. But that's fine because it's a quadratic thing. If I can write this as the fixed point of this quadratic problem subject to this constraint, known constraint. So I'm solving a quadratic problem up to a known constraint. If there was nothing here, I could just invert an inverse and that would solve the problem. Since I have the constraint, this is a classic problem. Nonlinear optimization has trust region method, trust region solve problem. And there's so many efficient ways to solve it. We actually end up solving this approximately. And all that it will give you is a bunch of matrix vector products, Maddie, which is costly, of course, but it doesn't give you any new gradient queries. You don't have to do anything. You just have to solve this approximately and have the overall cost at the end of the talk. But for the sake of argument, I'm going to assume that I have exactly solved this and I sort of like can get a delta n plus 1 that exactly satisfies this condition. Okay. So again, it's not a big deal because you're just solving a linear system of equation if you think about it over, normal. All right. So that's how you deal with the fact that delta n plus 1 shows up on the right-hand side. But the bigger question is how do you pick the estimator of the Hessian? I haven't said anything about it. And it can be arbitrary. So I'm not going to focus on, forcing Bn to look like Hessian. I don't care if Bn looks like Hessian or not. I'm just going to let my analysis tell me what to do. If you do this, if you use the hint function that I told you, and if you just do pure calculation, you're going to realize that your regret is the same term that you had previously, plus this additional quadratic term. Yn being the difference of the gradients, Sn being the difference of variables. And Bn was your choice of Hessian course. That's it. So you should pick Bn such that that term is as small as possible. Right? Basically. And then you should look at me, Aryan, like this is d parameters, like, and this d by d, you can solve it, you can make this actually 0 as small as you want. What's the catch? Why don't you do it? The catch here is when I pick Bn, I don't know Sn and Yn, right? I pick B delta n, my current point, and Bn, the estimator. Then I see the next point. Then I can compute the next gradient that I need for this calculation of Y and S. So again, that's another online learning problem, but in the space of matrices, right? The difference is like the loss function is going to be correct. That's it. So to update my B, I'm just gonna follow another online learning algorithm that solves this loss function, right? And gives me the smallest cumulative loss. All I have to do is to pick all these B to have this property that their eigenvalues are less than L1, because I know the Hessian satisfies this, and for some reason I need this boundedness. It's technical, but I can talk about it if you want. But all I have to do is to pick an online learning algorithm in the space of matrices with this loss function to update my B's. That's it. What's the easiest one? Online gradients. And the gradient of this loss function is also very nice and easy. It's like a rank one of them. It's pretty nice. Okay, so the thing is like for this online learning problem, there is no good fixed action. So static regret analysis will not help you. You have to go with dynamic regret analysis. I'm not going to bore you with this equation, I'm just showing it. But the important thing is you have to pick these competitor HNs to be like, these are the competitors, right? H1 to Hn, these are like the term that shows up in dynamic regret. What are the good choices about this H1 all the way to Hn is the actual Hessian. Again, I don't want to query Hessian, it's just for the sake of analysis of putting it. And if you replace those sort of like reference Hessians, reference matrices with the actual Hessians, you're going to get this cumulative loss. And that's the moment of truth. That's when you're on the board, you have done all your calculation, and you know that this is LNBN. Now I have to see how should I pick DKTs to get the bound that I want. So because I know regret depends on this, so I put this, and I would get something for my norm of gradient, because I know I have an explicit expression for regret in terms of all the problem parameters. And if I put everything together, this is the moment that I can figure out the complexity. It's a very stressful moment because you're trying to balance the terms and you hope that it's better be better than 7 over 4, better be better than 7 over 4. Like, and then when you do the balancing, well, optimization cost was on our side and it gave us 13 over 8, which is better than 7 over 4. The only caveat is like there's a D dependence, as I mentioned at the beginning of it. And this 1 over D, 1 over 4 over epsilon to the power of 13 over 8 is better than 7 over 4 if D is less than 1 over 1. All right, so that was the result. And this is the algorithm. What's that? How did the D? That's a good question. The D comes from this point. The initial term that shows up in the online learning, it can be as bad as L1D, because you have to bound this for Venus norm. There's another D that comes from the dynamic. That's it. And it's natural. If I had very good estimation of the actual Hessians, the D would be natural. But in the worst case, I keep it as that is. That's what it's about. And fundamentally, the D should come, right? Because you're estimating the precognition, so you should, in the worst case, you have to wait for D to. Like there should be some D dependence on. All right, so the algorithm is as simple as this. You solve a quadratic problem, like a trust region solve problem, and then you update B using this simple rank one update. There are 2 details that I omitted. How to solve this efficiently, which is something that I can talk offline if you want. It's part of the paper. And I really don't want to do projection on this in the space of matrices, because projection in the space of matrices means full algebraic decomposition. That is D cubic and cheap. I want to keep everything D squared. So, but there was a technique called projection-free online learning, which using a separation oracle, you can actually scale down all the eigenvalues to bring it down to somehow the same regret analysis works, and then everything stays at D squared. That's another 30 minutes. I'm not going to bore you with. We're all moving on the board, so there's no fun talking about. So, going back to your first question, what are the lower bounds? What are the upper bounds? So we finished this 13 over 8 on the board, swear to God. And I was comparing that with 12 over 7, which is the lower. 13 over 8 is better than 12 over 7. Did the calculation again. Something is wrong. 13 over 8. Shoot. What's going on? Going out to the lower bound, we realize that, oh, something is off, right? Then we realize, no, there's nothing off. The lower bound only holds in the regime that D is large. D is larger than epsilon to the power of minus 12 over 7. There is no universal lower. And in the regime that D is larger than this, since we have a D dependence, our bound instead of 13 over 8, if we replace D by this, you would get 1 minus epsilon minus 1 15 over 56, and this is worse than 12 over 7. Thank God. So we're not violating any lower. That raises the following question, right? The only lower bound that we know for the setting is for the setting that D is larger than 1 over epsilon to the power of 12 over 7. And we don't know any lower bound for D moderate, less than this threshold. So we even don't know if our bound is right, the upper bound, because there's no lower bound. So the lower bound is completely open.
How did they get that lower bound?
Be my guess. It's a long paper. It's using some chaining function argument. It's a very nasty construction of the audience. It's a very beautiful and hard paper, but yeah, there's not much intuition. I haven't contacted the authors if there's any way to extend it to lower dimension. They think it's not true. Anyway, so that was the lower one, and this is the only picture in my talk. I like it. So this shows the complexity bounds that we know in terms of 1 over epsilon and D. Okay. So the previously best known bound was 1 over epsilon 7 over 4, 2022, but there's no D dependence. If you had access to Hessian without any D dependence, you would get 3 over 2. Guess what's the middle point of the 2? 13 over 8, which is nice and cute. But we have a D dependence, right? So we sit right in the middle of the best thing that you could hope for, which is what if you had access to Hessian, epsilon-wise, and the previously best known bound. But there's still a lot of things to figure out here, right? So I have this D1 over 4 dependence. Can I come somewhere closer to 7 over 4, but at a lower cost of D? Like, for example, get something here or here. Or go somewhere here, get closer to 3 over 2, but maybe a bit more costly in terms of D. Can I do that? I mean, if you can come this way, perfect. You improve both epsilon and D, right?
So you also got some intermediate result where you had 7 over 4.
Yeah, but it
But
wasn't
that didn't have
really
D.
the previous bound.
Yeah, and there you didn't have D.
I didn't have D, no.
You did.
Yeah, no, it was matching this, which was fun but unsatisfying. It didn't have any precondition, that's why it didn't have.
Oh, that's why.
Right. So that's where the upper bounds land escape is. So if you can improve it, I would love to chat. Thank you for your attention. So this is the strongly convex result, the convex result I briefly mentioned at the beginning, and the main result I present today is this extension to a non-convex case. Sorry if I went over time. Thank you so much for that.